So before getting to the whiteboard, let's talk about some concepts that you need to be aware of, and also let's talk about why you need to be aware of those. First of all, let's talk about watts. So I'm not going to give you a headache talking about that watt is the amount of energy in joules needed to perform a 1 Newton move on an object. All right, let's make it simple. It's a measure of electrical energy. How much electrical energy you consume, how much electrical energy you send, or how much electrical energy you receive. It's just a measure of energy. Okay, watts. Of course, if you work with Wi-Fi, we're not using a lot of watts, so we'll be using milliwatts, which is 1,000th of a watt. Okay, so that's a concept will come very often. Now, some references. If you listen to the radio and you have a broadcast radio, their station antenna, of course, it's not using the Wi-Fi frequencies at all. It's a lot lower frequencies. They typically send a very, very powerful signal because it has to reach very far. It's in the order of something like 50,000 watts. So that's a radio station, right? If you look at your microwave oven, you're more in the 1,000 watt type of range. Now, if you look at your access point, the maximum power an access point can be sending is 100 milliwatts. Actually, it typically goes lower than that. It can be 1 milliwatt. So imagine that. You have a microwave oven that sends 1,000 watts, and you have your access point nearby that may be operating at 10 or 100 milliwatts. Imagine if you have a 0.01% leakage on your microwave oven. That amount of energy that spreads out of your microwave oven is still more than the total output of your access point. Does that matter? Yeah, of course, because you'll see later on that those two work sometimes on the same frequencies. The frequencies that microwave ovens use are some frequencies that we use with Wi-Fi as well. And when both are in the same area, typically Wi-Fi does not win. So watts is something you need to be aware of. The second thing you want to be aware of is the decibel scale, because we'll be using it a lot. So that was invented, more than a century ago by the Bell Labs. And what they were doing was designing some phone systems, and they were designing some phone booths where you would be sending some voice sounds into an amplifier that would be sending some energy of that sound over a wire. And what was interesting for them to determine is how far can I go, pick up the line, listen, and hear the sound in a way that makes sense to me. And that's the origin of this decibel scale. Where is the point where I lose much of it? And of course the question is, much, what does that mean? What is much? And they decided to measure in half. So where's the point where I lose half of the energy I input in my phone initially? Where's the halfway point? Where do I lose half of it? Where do I lose again half of it, etc.? So they were working in halves and halves. And that gave them the decibel scale. Of course, it was initially designed for values, but the idea of reasoning in half and then half, or of course twice and twice, is interesting in many, many fields. The Bell Laboratories use the decibel scale for sound, but we use the decibel scale for many other things. We just put another unit behind decibel to know that this is not talking about sound, it's talking about some other type of measurement. For example, volts. You would say decibel volts. How much volts do you lose? Half of them, etc. But also watts and milliwatts. How many milliwatts you get and how many milliwatts you lose. And that would be dBm. That's a value we use a lot. So why do we need it? Well, simply because the decibel scale is nice to compare values. Because you remember, I never told you how much sound you did put into that phone booth initially. Because it doesn't matter. What matters, regardless of your volume when you speak in that phone, where's the point where I lost half of the volume of what you said? If you speak louder, what I'll get at the half point will be more than if you speak more softly. But in both cases, you lost half of it. And this is what is important. And this is why we like it a lot in Wi-Fi, because if you take, for example, your microwave oven and your access point sending at 1 milliwatt, what matters is that the microwave oven is 999.9 watts stronger. And if you just say it that way, you say, okay, that's a lot of nines, but what does that mean? What that means, it's 10,000 times stronger, or 100,000 times, depending on how much energy you use in your antenna. And this is what we care about. How much more in terms of times are we comparing things? And this is also very useful when you receive energy from access points. You'll see that you receive thousands of milliwatts. It's very weak, very faint. We'll check that together on the board. But what matters if you compare what you get at one distance to what you get at another distance. If you look at those numbers, you'll say, well, in one case I received 0.0000565, and in the one is 0.000000527. Okay, it's very weak in both cases. But if you compare with the decibel scale, you'll be able to say, oh, that one is 10 times weaker. And that tells you a lot more than just telling pure numbers. That's why we use decibel a lot. And to work with decibels, you can find online scales that give you some ranges between milliwatts and dBms. But what matters is the logic behind it. And the logic is that because it's a logarithmic scale, every time you have exactly the same amount of energy you send on the other side, there is no change. Nothing more, nothing less. And the way we say that in the decibel scale is to say there's 0 dB difference. It's the same here and there, 0 dB difference. So keep that in mind. 0 dB does not mean no energy, right? It means no difference between your reference points and what you're looking at now. That's the first rule. The second rule is what we call the rule of threes. Every time you have twice as much, you double, you add 3 dB. So if you have 1 milliwatt and you double, you have 2 milliwatts, you add 3 dB. So that's going to be 3 dBms. Again, more on that on the board. So every time you double, you add 3. You double again, you add 3 again. And this is where it becomes a little bit strange. If I have 1 milliwatt and I look at the other side and also have 1 milliwatt, there is 0 dB difference because it's still 1 milliwatt. If I have 1 milliwatt going through an amplifier, and here I have 2 milliwatts, well, it's twice as much, so I have 3 dBm. Remember, twice as much is plus 3 dB. If my amplifier goes up a little bit more, and instead of having 2 milliwatts on the other side, I have 4 milliwatts, then I double once, and I double twice. So it's going to be plus 3 dB once, and plus 3 dB a second time. That means I'm going to have 6 dBs. So be careful, we'll come back on that on the board, but every time you double, you add 3 dB. You don't multiply, you just add 3 dB. Of course, every time you divide by 2, you remove 3 dB. It's the same logic on the other direction. So that's the second rule, the rule of threes. Doubling is plus 3, dividing by 2 is minus 3. And the last rule you need to remember is the rule of tens. Every time you multiply by 10, you add 10 dBs. So if I inject 1 milliwatt on one side and have 10 milliwatts on the other, in the other side of my amplifier, I'm adding 10 dB to my signal, 10 dBm, because I'm talking milliwatts. And of course, the same minus and plus rule as the threes applies. If you divide by 10, well, then you lose 10 dB, so you remove 10 dB. Times 10 plus 10 dB. You divide by 10, you remove 10 dB. You double plus 3 dB. You divide by 2, you remove 3 dB. If you remember those rules, you'll be safe everywhere. The other thing you may want to do is to always start, if you can, with the tens, because you'll see it's easier to work with the tens first and then work through the threes. It's also because that rule that we are talking about here are approximations. Again, if you look online and you'll see exact tables, you'll see that we round up things a little bit. So we get closer to the real result by starting with the tens first if we can, than if we were to start with the threes. So as much as you can, start with the tens, and then when you can't do tens anymore, move to the threes. Okay, so that's the general rule. Of course, we are talking here in many different units. One of them is the physical energy of current that you send through a cable. And because we're talking in milliwatts, we'll be talking about dBm very often. Our reference is 1 milliwatt. So that's our reference always when we talk about dBms. So if I say 10 dBm, I'm saying 10 dB compared to my reference, which is my 1 milliwatt. And 10 dB is 10 times the power, and my reference being 1 milliwatt, that is 10 milliwatts. If I say 20 dB, I'm going to say 20 dBm to make sure that you know I'm talking about milliwatt as my reference. It's 10 times once and 10 times a second time. And that's why I add 10 dB once and 10 dB a second time, 20 dBm. We'll check that more in detail on the board. But be careful, every time we say dBm, we talk about 1 milliwatt as being the reference. So that's one possibility, right? Talking about milliwatts, 1 milliwatt as being reference. 0 dBm is exactly 1 milliwatt. If you double the value, 3 dBm, that's going to be 2 milliwatts. And of course, it works in the tens as well. When you add 10 dB, that means you multiply by 10, reference 1 milliwatt, you have now 10 milliwatts.